Okay, hello class, sorry I can't be there today. Hopefully we're all on our best behavior for the sub. To start, we're looking at 11.3, geometric means. Your first definition is talking about an arithmetic mean. That is the sum of a set of numbers, and it's divided by the number of values in the set. So if we were figuring out test scores and I wanted the average, I wanted the arithmetic mean, those words mean the same thing. I'm going to add up all of your test scores and divide by the 27 of you there are. So I'm going to add up 27 tests. Since I added up 27 things, I divide by 27. So arithmetic means that we're using arithmetic first. We're using addition here. So when it says what is the arithmetic mean for the numbers listed, we add them all up. Since we added up 10 numbers, we divide by 10. So for our numerator, it ends up being 102. And when we divide that by 10, we end up with 10.2 for the arithmetic mean. We have something that's called the geometric mean. Instead of using addition with the arithmetic mean, we're using multiplication. This is the nth root of the product of n numbers. So all that means is if I keep multiplying, let's say I start with two numbers, if I multiply those together, if I took a times b, since I'm multiplying two numbers together, I take the square root of it. If I was multiplying three numbers together, I have to take the cube root of it. If I wanted to find the geometric mean of 4 times 5 times 6, multiply those together, take the cube root. If it was 100 numbers, take the 100th root. So here's an example of what a geometric mean turns out to be. It ends up in a proportion. If we have 2 out of the 10 equals 10 out of 50, the number 10 is really the geometric mean of 2 and 50. If we take 2 times 50 and we want to find the geometric mean, we're taking the square root of it. If we take the square root of 100, well, that equals 10. This 10 is a numerator and a denominator for both of those values. So if we had a and b, we would have to take the square root of a times b. So if I asked you to find the geometric mean of 12 and 3, multiply those two numbers together. Geometric means multiplication. And since it was two numbers we multiplied together, we are taking the square root. 12 times 3 is 36. When we take the square root of 36, we get 6. So we use geometric means in things like statistics and finance and science and investments, but it's also going to appear in geometry. Geometric mean, geometry, obviously they go together. Specifically, we see this in right triangles. So here in our picture, A is going to be the geometric mean between B and C. This comes from the proportions. So when I think about these triangles, I can split it up into two smaller triangles. I'm going to draw those two smaller triangles the same. I can see in one triangle, I have C as my long side, A as the shorter side. I see in my blue triangle that A is now the longest side. B is now my shortest side. So when we think about a proportion and we do the short leg over the long leg, that means from the triangle in red, we'd have A over C. From the triangle in blue, we'd have B over A. Okay, this is a geometric mean. We have the same number in the numerator as the denominator. When I cross multiply to solve for a times a gives us a squared. Other way, b times c. So to solve for a, we'd have to take the square root of b times c. That's what they just said here. That was kind of like a mini proof. All right. So another geometric mean occurs between a side of a right triangle and the hypotenuse and a side adjacent on the hypotenuse. Really what we're trying to say is, here we broke this triangle down into the two smaller triangles, the blue triangle and the red triangle. In this next example, we're going to split the triangle into one of the small triangles and compare that to one of the big triangles, or the whole triangle. So if I look at my triangle in red, I can see that E is the longest side, and now D is actually a hypotenuse. I'm putting that opposite my right angle. When I look at that full, sorry, I'll make these look more similar here. When I look at my full blue triangle, the whole triangle, I see that I want to compare a long leg, which is now D, and the whole hypotenuse, which has length F. If I have a long leg and a hypotenuse in each, we can set up a proportion. I have my long side of D over the hypotenuse F, and I have the long side of E over my hypotenuse D. When we set this up correctly, same number on the numerator as the denominator of the other fraction. When we cross multiply, B squared equals EF. So if I'm solving for D, I'm taking the square root of EF, just like it says here. Similarly, we could also compare this triangle in green to the triangle in blue. We're taking the second small triangle, relating it to the big triangle, and we'd end up with H equals GF. So for 11.3, these examples, we need to draw two triangles. When we do this, you're either comparing a small and a small, or you're comparing the small to the big triangle. How do we know which ones to use? I'm going to draw all three triangles to help us narrow this down. So if I draw my triangle here in green, I have a short side of A, a long side of 5. Okay, I could try comparing this small triangle to the big triangle. If I look at the big triangle measurements there, all I know is the hypotenuse. I could figure out that that was 9. I don't know those side lengths. That's why I do not want to use the blue triangle. I want to use the other small triangle. So if I use that other small triangle, I'm doing small and small here, I have a short side of 4, a long side of A. I have a short side and a long side in each. I can take the short side over the long side, short side over the long side. Cross multiply. A squared equals 20. When we take the square root of 20, A is really about 4.47 units here. Okay, if I look at B, I'm going to find my variable there. I'm going to use this triangle. I have to use a triangle with the variable. This time I have a hypotenuse and I have a long side. When they give me a hypotenuse and a triangle, I have to use the big triangle. Now I can see that x is the long side in that triangle, and my hypotenuse, if I add up 3 and 5, gives me 8. Remember, I cannot use this green triangle. I cannot do a small and a small, because if I draw that out, I only know that the short side is 3. I know nothing about the hypotenuse. I don't know the long side. That's why we're not using that small triangle in green. So when we go x over 5 for the hypotenuse over the long side, we'll go 8 over x for the hypotenuse over the long side, cross multiply, x squared equals 40, take the square root, we're finding the geometric mean, x equals 6.32 units. For C, here's my variable. I need a triangle that has 2 side lengths and the variable. So I'm using the big triangle. I have a short leg of y. I have a hypotenuse of 10. Okay, we could try to use this triangle here in green. All we know is the long leg is 6. We don't know any of those other sides. That does not help us set up a proportion. So we cannot use that triangle in green. That means we're down to just the triangle in red. So this time, my hypotenuse is y, and I can find the short side length by taking 10 minus 6, the whole side length minus the 6, to give us 4. Now I can take the short over the hypotenuse equals the short over the hypotenuse. You set them up correctly if you get the same thing on the diagonal. It will not always be a variable on the diagonals. Y squared equals 40, just like last problem. When we took the square root of that, we end up with 6.32. For D, okay, we're going to set up our triangles. Maybe now we're starting to see which triangles to use. I need triangles with 2 side lengths. This triangle in red, I know 2 side lengths of it. I will redraw that. I know my long side is x. I know my short side is 5. I know 2 side lengths of this triangle in green. I have to use that triangle. I know my short side is 3 and my long side is 5. That way my proportion looks like short side over long side, short side over long side. If we did this correctly, we have a numerator and denominator that match. This is an example where it's not always the variable. 5 times 5 is 25 equals 3x. When we divide by 3, x is really 8.3 units. We're going to skip E. But when I look at F, we're going to figure out Which triangle can I find two side lengths of? If I look at the big triangle, I know the long side and the hypotenuse. I know two sides. I need to use that triangle. If I look at this triangle in red, do I know two side lengths? I know one is y. I don't know either the height or the hypotenuse. That's why we do not use that red triangle. We don't know two side lengths of the red triangle. Okay. What we do know is that, I'm trying to undo. In our triangle in green, we know two sides of this triangle. We can see that the hypotenuse is 4, and we can find this leg here by taking 12 minus y. That'll be the short side of the triangle. When that happens, we now have the short side over the hypotenuse equal to the short side over the hypotenuse. This is where we need to be really careful when we cross multiply. Here's our diagonals that are the same. That'll be 16. Here's the 12 times the quantity 12 minus y. That way I remember that both of these terms get multiplied by 12. A lot of times we'll just see 144 minus y instead of the 12y. So here I'm going to subtract 144. You might be nervous about these negative numbers, but we'll see that when we have negative 128 equal to negative 12y, and we divide by a negative 12, we end up with that positive y value, which is good since we're talking about side lengths. What did I say? We got 10.6, or sorry, 10.7 units then. So we skipped E. I'm just going to use it to summarize for those of you who are still out there, still having some questions. You can always set up 3 triangles. If that's what helps you and you have to narrow it down to 2, go for it. I see the triangle in red. I see a small triangle. Here's that same small triangle. I have a short side, and in this case, a hypotenuse. I'm looking for another triangle that gives me the short side and the hypotenuse. I see another small triangle here. So I'm thinking, do I have the short side? No. Do I have the hypotenuse? Yes. But since I don't know that short side, I cannot use that triangle. That means that I'm using the big triangle. Okay, I have my short side of 6. I have my long side of x plus 15. I could figure out if I added those together. All right, here's another way that might make sense to some of you. If they give you something on this line here, if they give you that altitude to the hypotenuse, you have to split it up into those 2 triangles. You would use the red and the blue triangles. Since they didn't, since they gave you the side, you're using the big triangle, the side and the hypotenuse. You'll be able to find another triangle with the side and the hypotenuse. Hopefully that helps. We're going to stop here with notes. There are some more additional examples on Canvas if you want to copy them from the notes key that's already uploaded. Otherwise, you can start your homework. We are done with 11.3, so whatever examples you want in there, copy those down. Even if they say day 2 examples, tomorrow we're starting 11.4. For tonight's homework and your 11.2 homework, since we didn't get a chance to talk about that today, those both have the keys and the work are shown on Canvas. Maybe that'll help answer some questions if you can see the work that was done. Thanks. Thanks.